Okay, 7:30, let's get started. So tonight our discussion topic is the first part of the parallel architecture organization, I believe. Let me just double check with the syllabus. We are in module 8, yeah, parallel processing architecture 1. And in this module, we are describing different abstract concept of how we can improve the performance of computing system. Uh, and there, in this specific lecture, we have tried to classify this parallel system according to their characteristics, like a multiple instruction, multiple data system, multiple single instruction, multiple data system, etc., etc. One thing to note here in this case, this MISD system, multiple instruction, single data system. So I'd like to point some notes apart from what the video tells about this system. I believe in the video we claim that this is more like a laboratory uh, systems for research and stuff like that, not practical usage. However, there are like certain school of thought of some systems to be MISD classification. So it's practically really depends on how you look at the system. Let me try to explain what I mean by that in the Google Jamboard. So, so by definition, your multiple instruction single data system should look something like this. Let's say I have multiple processing unit, data processing unit, PU1, PU2, PU3, and PU4. And presumably, let's say they are uh, executing different instruction, like instruction 0, instruction 1, instruction 2, different instruction, but on the same data, same data. So this is the conceptual view of this is a multiple instruction single data system classification. Some actually consider, for example, like fault tolerant system. Tolerant systems as MISD. But I say this is kind of a very weak classification in that sense that in a fault tolerant system, what happens, like same resource is like replicated multiple time. For example, this processing unit 1, 2, 3, 4, they are basically are replication resource of each other, and they practically work on the same instruction, like same instruction I, okay, same instruction I. The advantage of that, if let's say one of the system goes down, like it's a physical electrical system, so it can break down, right? So, but fault tolerant system, the target is that even if one resource is down, it can still compute the result because there is this duplicate resource operating in parallel, and system picks up result from a from a subsystem which is not gone bad, like which is not broken, right? And that's the concept of the fault tolerant system, and it is deployed to many critical system level areas. For example, like real-time controller of the electrical cars, right? There are replication or duplication of resources so that at least at the compute level, if one component fail, it does not cause a car crash or something. Similar goes with the rocket launching system and rocket control system. All this critical system actually goes with a fault tolerant system design. So main view is that we replicate resources multiple times, and then so that if one subsystem is broken down, we pick up from the corresponding duplicate resource. But from the strict classification perspective, my personal opinion is that we should not even call this as a multiple instruction single data system, because they are actually processing the same instruction. It's just a replication of the operation, nothing like that, nothing else. Um, However, like in recent days, MISD system actually got traction. I don't know if you heard of this thing from Google, is TPU, Tensor Processor Unit. So Tensor Processor Unit is, you can search in Google and please read through the Wikipedia page. They are quite a good article on that. But in overall, this is more like an AI area, and there are many small and startup companies are nowadays working on this AI chip. Like AI is no longer bound in the software domain, but they're trying to come up with a vision chip, like other artificial intelligence chip, and where it is actually, to my opinion, it's truly an MISD system. Because, for example, if we are developing a neural network, for example, right? Neural network, just in a very high level concept, it is something like this. Like we have these processing nodes, okay, processing nodes, and let's say informations are coming up, information or data, let's say D3, D2, D1, D0, and they are fed into all this processing node. They're all fed into all this processing node by theory. Okay, they're all connected, all connected. Okay, so one single data is actually being fed into multiple processing node. Okay, and their outcome will also like be fed into like all other nodes. So this is basically a practical neural network studies. And if you go with that study, you'll see like how this neural network is done. On the hardware sense, these nodes, processing nodes, these are all our processing units, all our processing units. And in that case, it can be truly classified as multiple instruction single data system, because your single data is fed into multiple unit, which is processing this data differently, as I see. So that's one thing I want to mention you about this classification of the parallel systems. Also, there are like high level diagrams and schematics and there in this specific lecture and next lecture. But my suggestion would be that don't try to memorize it. Okay, you need to understand basically what is the core concept. And this is not the only concept that is there. It is, as I said, it's an open area, and you can come up with your own architecture, own strategy to make a parallel system and to boost up the performance. So all these lecture slides all have some guideline some example, typical example, what people think, what way it can be thought, and so on and so forth. So the concept is important. Understand that. And if you understand that, just coming up with diagrams and all this stuff is not very difficult. And of course, like with the online exam and everything, I won't be able to ask you to draw a diagram, so you're kind of safe there, but at least try to understand the concept of that rather than memorizing things there. All right. Questions so far? Anyone? Okay. The third point is basically I want to say that you will see there are, like in this lecture and next lecture, there is mention of the multiprocessor system versus multi-core system. Conceptually, they are same. Conceptually, they are same. Physically, they are different. Okay, physically, they are different. What do I mean by that? Multi-core versus multiprocessor system. So multiprocessor system is basically where you actually open up the, if you open up the computing box, you will find like maybe this is the motherboard. Is hosting, let's say, 4 chip, like maybe like, let's say, for example, Intel, like Pentium 1, okay, Pentium 2, Pentium 1, the second instance, Pentium 1, third, Pentium 1, fourth instance. So on the motherboard, you will find 4 physical processor chip sitting there, okay, and they, each of them are like, in our sense, is a single core system, and this is more like an parallel or multi-processor system. And I'd put a note there, it's the old style system. Okay, when there is like, we can actually host on a piece of silicon only one processor, one processing unit, and each chip is just one single scalar processor. In that scenario, people actually, engineers came up with this multiprocessor system at the board level, motherboard level, where you actually physically see 4 IC, 4 integrated circuit, 4 chips are connected through the motherboard wiring. Whereas multi-core system, on the other hand, is the same concept. Let's say it's a 4-core system, core 1, core 2, maybe they are Pentium cores, core 3, core 4. Now this guy is a piece of silicon, same silicon. So this is one single chip. So if you open up the system box, and you will find one chip on the motherboard, but internally they have these 4 processors connected together, and these are the multi-core systems by concept. Conceptually, they're same. Practically 4 processors in parallel, they're crunching the data, they're crunching the numbers, following the instruction, executing the instruction, but like physically, they are different in this sense. Like one is, you see on the motherboard, you will see 4 physical processor, physical IC, you'll see that on the board. But multi-core system, you'll find only one physical processor, but inside the processor on the same silicon, there are 4 processor, which basically we call it a core nowadays. Question? Okay, now the other part is a little bit of detail. Like we talked about this SMP symmetric multiprocessor system, and one of the architecture is like a bus-based architecture, and we just touch on that. Let me elaborate a little bit on the bus-based architecture, which is not probably explained in the slide or lecture videos that clearly. Let me see. Probably you have more question on that, this bus-based system, but let me see if we can pre-address that before you even ask those questions. So in a bus-based system, there are like many, like this is basically very one common architecture, and we'll find many bus-based systems. For example, AMBA, IDE is more popular, and probably most popular is USB, Universal Synchronous Bus. It is everywhere, like all the devices, all the handheld devices, mobile phones, uh, game console, everything has these USB, at least one USB port there. But this is also a bus-based system. So the whole concept of the bus-based system is this. A bus is a very passive component. It is just bunch of wires, just a bunch of electrical wire. Let's say some copper wire is connected. And there are multiple of them. Multiple. Like maybe like 64, 128, 256, who knows? Like some n bits. And there are, let's say, some processing unit, let's say in terms of core, like core 1, core 2, core 3, core 4. They are connected to this bus. They are exchanging information with this bus. And remember, these are all electrical connections. And not only them, there are other, like these are processing unit. These are all processing unit. Processing unit 1, processing unit 2. They are the active element in the system. And there will be some other elements like memory, for example, or IO devices. Okay, so they are also connected to this bus. They're also connected to this bus to exchange information within themselves. Now you see, the immediate problem becomes if two of the element, let's say core 1 and core 3, they are sending data or information onto the bus. If they're doing at the same time, it will be electrically contaminated with each other, right? So we need to prevent that, right? So for that prevention, there is one specialized component called bus arbitrator. And the process is called bus arbitration process. What does it mean? All the active element, that means this guy, okay? And they basically can initiate a transfer of information through the bus. So all of them has a request channel. So all this request comes to the bus arbitrator, and bus arbitrator has granting signals going to them. Okay, and it usually maintain a queue, request queue inside it, so that anyone can actually go and request, and that request, so this request are pushed into the queue fashion, and that is first in first out structure, hardware structure, first in first out, and they can have actually implement more other sophisticated strategies, like it can put some priorities, set some priorities to one processor to the other. System can do that and ask bus arbitrator to prioritize their request. It can be done in a complex way, but simplistic things, just fast in, fast out. So what they do is basically whichever is in the head of the queue, it basically dequeue that and send the grant signal to the corresponding processor. So let's say it's now on the head, it has request from core 4, so they will give a grant signal for the core 4, and then only if an active element gets a grant signal, after that it can initiate a transfer through this bus, either like maybe to the IO device or to the memory device, and so on and so forth. Only it has been granted. Okay, and then I think there is one more important signal is basically called a down signal. So each of them is connected, which specifically say that, hey, my request, my operation is done, I'm releasing the bus. So this is like a done signal. So once this, I don't understand. Once this active element is done with this information exchange within the memories and IO devices, or even in some cases between the processor themselves, they actually raise the down signal to the bus arbitrator, and then bus arbitrator went to the next candidate for whoever is requesting for a transfer. Okay, so once the transfer, once a core is send a request to the bus arbitrator, then that core waits actually till it gets a grant. It just sit there idly till it gets a grant, and then once it is granted with the bus, then it initiate that corresponding data transfer to the other devices. So this is the like very general strategy that any bus-based system deploys. So another point to be noted here. Now see, this bus-based system, all these components are connected to the same electrical system, right? And there can be not only memories, IOs, there can be many other types of passive devices that a core or processing units wants to get holds of. Then the point become how it address, like how it tells, like they're sending generic information onto the bus, but how the memory knows it request has been sent to it. or a specific I/O device like keyboard or mouse or even display unit knows that some request has come to them. So it is done by like a packet-based communication. And it follows bus protocol. That is one point, bus protocol. And this is like information is sent in a packet, like a packet which has data definitely, and also has target ID of the device, target ID of the device. So each device in the system actually has unique IDs embedded into them, and system know, the active elements know what ID it is trying to communicate, and it puts that ID into that data packet, into that communication packet, which contains the data information, may contains the instruction that, hey, give me, for example, it can tell this memory that, hey, give me data from this address to that address. Then memory start transferring those data into the bus, and it assumes that that corresponding processing unit will pick up that data and listening to that bus on that system. So we are kind of going towards the communication protocols and communication system on this bus-based system, which is very, very similar. Later on, you will see there is this CCX system. There is another system. This is a little bit complicated than bus-based system called cache crossbar system. We'll see towards the end of the memory hierarchy caching system. CCX system is more like a network communication. If any one of you have gone through the network communication class, like network protocol, TCP/IP protocol, and all this stuff, it's very much similar to that concept, that it basically communicates among within the device as a network protocol. Okay, so that's the concept I want to discuss with you. Any question? No question, seems like. So, yeah, I think then we can, actually, I don't have any more things to do tonight. How is your project going on? Project 3?
Almost ready to start.
Almost ready to start? Okay, please start it. As I think somewhere I explained in that project guideline that there is like time consuming way, like which is you are basically replicating all these 32-bit components in the Verilog code. That is like you have more typing, one way. Another way is that more programmatic way of structuring that structural Verilogs. And that is like easier, I don't see easier, it is less to write, hard to debug. So you need to choose your poison. Either you write more, then less headache on the debugging side, versus less writing, but more headache on the debugging side if there is any issue come up with those systems. So please start early. You will face trouble, you will face challenges in the project 3 as well, because it's a tedious writing project. It's code of the, because we are developing 32-bit systems, so that's why you will be actually replicating codes like maybe 32 times, all the steps. So please watch out that you may need more time. But I would say conceptually it is easier than project 2. Okay. Other questions?
I started project 3 and I did like the first lab, like lab 11, and that was the one where you do like a half adder and a full adder, and then like a 32-bit like adder and subtractor. You asked us to add like a test bench for a half adder. Should we also add one for like full adder and also the 32-bit adder?
It's
Like just
up
everything we do?
it's up to you. As long as you are confident your component is doing fine, uh, it's okay. Remember, like, I don't actually take the test bench from you. It's for you, and you need to describe it in your report that what testing strategy you test and why do you think your component works fine, right? And I test with my test bench. So as long as you are satisfied with your testing, that you are confident your component is working, I'm okay with that.
And then similar to project 2, can we share our test benches with
Yes.
each other?
Yeah, sure.
Okay.
Oh, oh yeah, sorry. So I wanted to start the multiplier. I was wondering if you have like any tips on how to like start it, because it's like we have to do the combinational one, right? So I was just like confused on like how to like start it.
You need to follow the exact that combinational multiplication. Remember, it has this 31 adder with 32-bit and so build up in a step with that. And if you want to go with that programmatic way, it will be much trickier. Okay. Other strategy can be, instead of typing all these things, replication code and connection, you can do a little bit scripting, like whatever scripting language you know, like Python or JavaScripting or anything that can automate. And you know the patterns, right? How your one component is connected to the other, then you can actually like put it in a script fashion in a loop and spit out the Verilog code for you. That can be other way to do it.
Okay, thank you.
So for the data path, the stack pointer and the program counter registers are like implemented gate-wise. And how do we like initialize those to the values that they have to start at?
So remember, you have this preset reset,
Yeah.
right? You can actually either you can hardcore, like when you are instantiating those, let's see. So you need to actually make it, if you reset, so idea is that if you reset, if you send a reset signal to the program counter or stack pointer register, it will not reset to 0, but it will be resetted to some values, right? So these values are what? These values are basically either 0 or 1 at the bit level, right? 0, 1, 0, 1. So let's say you are sending a reset in a multi-bit, that 32-bit register, but inside that register, you are either connecting that reset to the preset if you want to make it initialize to bit 1, you connect that to the preset and connect other signal to the reset, and vice versa. So you get my point?
Oh yeah. So basically, we have to create like a custom 32-bit register.
Exactly.
Okay. Thank you.
Another idea would be like make a parameterized component. Okay, parameterized component means like, remember, like there is a dot param statement in the Verilog, and you can pass some parameter. It is possible that your hardware component, your simulation model can take a parameter value and set up this preset reset accordingly. Okay, just think of that way as well. One is definitely straightforward way is to make these custom registers for program counter and register file, stack pointer. Other way would be create a parameterized component and pass the parameter as that initialization value. That would be a little tricky, but interesting to think of. Okay, think I can probably think also and see if we can. I'm just suggesting. Okay, so maybe I can give you some more pointer next time, but just remind me. Okay, if we don't have any question, then we can
Uh,
probably.
sorry.
Yeah.
I have a question about the implementation of the logic components.
Mhm.
Do you prefer us to implement it in data flow modeling or behavioral modeling?
Data flow, like it's a logic gate. It's not not data flow, neither behavior. It's pure logic gate.
I see. So for example, like the decoder, we should do it in like the gate level modeling, as in
Yes,
we
yes,
just
data
assign.
path.
Okay.
Yeah, anything related to the data path, your ALU, your registers, your register file, your data path, multiplexer, everything has to be boiled down to a gate level, like an and those kind of things. Only for the controller, we will still use the behavior level. Controller is too complex to be on the gate level implementation.
Okay. Thank you.
Anything else? All right. Good night then, everybody. See you in next week. Work on your project.